So let me start. First of all, the problem was the following. In the previous lecture, I considered the problem of moduli spaces for compact Riemann surfaces. So let me have a compact Riemann surface gamma of genus G. And first of all, what is known that if you consider topological classification, it's full information. You have Riemann surface, and its topology is completely determined by the genus. But if you consider the Riemann surfaces from the conformal point of view, or from the point of view of complex structure, which is equivalent, then we have, for example, different tori. Two tori may be not equivalent, may be equivalent. So we have the space, moduli space for Riemann surfaces. You have two objects, Teichmüller space and moduli space. Moduli space is the factor of Teichmüller space by the group SP and GZ. And the problem was to calculate the dimension of the spaces. And it was proved that the dimension of the spaces is zero for G equals to 0, 1 for G equals 1, G minus 3 for G greater than 1. Of course, you talk about complex dimension. We proved it. How we proved it? First of all, we considered infinitesimal deformation of complex structure. First of all, in dimension 1, there is no difference between complex structures and quasi-complex structures. Because what does it mean, complex structure? It's multiplication by I at each map. Quasi-complex structure is multiplication by I in the tangent maps at each point. Of course, if you have multiplication in a map, you have multiplication at each tangent space. In dimension greater than 1, the opposite is not true. You may have multiplication in each space to I, but it may be not generated by global. But in dimension 1, it's equivalent. In fact, we proved it when we introduced isothermic coordinates. Therefore, there is no difference between complex and quasi-complex structures in dimension 1. What does it mean complex structure, quasi-complex structure? Since we have operator D, first order operator. dy. It's vector field. A and B are complex valued functions. Then we have D and empty. There is a pair of vectors. Assume that they are linear independent, where they are positively oriented. Then you can introduce following operator I. For example, simplest example, the operator dz bar. 1/2 dy. What we have in this case? Re zero. Therefore, complex structure maps first this vector to this one, and this vector to minus this one. Therefore, I is the following matrix in these coordinates. So it's okay. Therefore, if we have first order operator with these two conditions, these two vectors are linear independent, and this pair is positively oriented, then we have a complex structure. Or if negatively oriented, you have to invert the orientation. And vice versa. If we have operator I in the tangent space, we can take any operator d1 and reduce d is d1 plus I Здравствуйте, hello. Oh, okay. Let me repeat. How we define complex structure? Of course, what does mean complex structure? Of course, the main definition is if you have a holomorphic atlas of maps, coordinates. But since we don't have holomorphic atlas, we can introduce quasi-complex structure. What does mean quasi-complex structure? You have multiplication to I in each tangent space. In each tangent space, it means that I is any operator with following properties. I square is minus 1, and maybe it's and if assume that we have a first order linear operator complex, you consider the real and imaginary part of this operator. It's a pair of vectors. Then we can introduce I in the following way. I applied to this vector is this vector. I applied to this vector minus this vector. So we define a quasi-complex structure. At each point in the tangent space, we have operator I. We have a quasi-complex structure. And remember, we proved that in dimension 1, if you have quasi-complex structure, you can write Beltrami equation, you can introduce isothermic coordinates as solutions of this Beltrami equation, and automatically it means that we have a complex structure. We introduce complex coordinates. What we have done? We considered such operators. Starting from operator, we solved Beltrami equation. And solution of Beltrami equation is complex coordinate. It means we have a complex structure. We proved it. But of course, it's valid only in dimension 1. In higher dimension, we can write Beltrami equations, but they are not necessarily compatible. Dimension 1, we have no composability problem. Therefore, if we have an operator, starting from operator, I and B are complex valued, then we can define quasi-complex structure, which is automatically a complex structure. Vice versa, since we have a quasi-complex structure, then we take any first-order operator, we introduce D in this way. For example, because if your standard complex structure is this one, this vector is mapped to this one. So I consider the following example. What does it mean standard complex structure? Is multiplication by I. It means that it maps this vector to this one. So it's this. Therefore, if we have a quasi-complex structure, we have a Beltrami operator. D. So what summary? how to describe complex structures. Either we can introduce quasi-complex structure, it means operator I in each tangent space, or equivalently we can write a first-order differential operator. Now, what does it mean, deformation of complex structure? So is it clear that complex structures are equivalent to Beltrami operators? And of course, we can replace operator. But of course, simple observation is that this, since we have operator D, we have operator D bar is alpha of xy D. We have two operators. Of course, the space of solution D of course, you agree these two equations are equivalent. You multiply operator by some function on the left, these two equations. You agree? I'm sorry, I answered your question in some sense, that as soon as we have a first order operator, then we introduce a real imaginary part. There's two vectors at each tangent space. Then we introduce I. Therefore, this formula defines quasi-complex structure. Vice versa, if we have a quasi-complex structure, we introduce this operator. D is D1 plus I D1. D1 is a vector at each space, and I is operator in the tangent space. Therefore, quasi-complex structure is equivalent to Beltrami equation. Remember how we introduced isothermic coordinates. We wrote Beltrami equation, solved it. So, okay, first step. Now, we would like to deform complex structure. If you have isothermic coordinates, the complex structure is equivalent to the operator. D is equal to Z bar. You agree? This operator defines complex structure in complex coordinates. Now, we do the following. We change complex structure, but keep the same coordinates. Therefore, the coordinates are not isothermic anymore. They are not complex anymore. We keep the same coordinates, but change complex structure. It means that we introduce new operator. D is D Z bar plus B and dz. So, variations of complex structure, epsilon, of course. We write epsilon. Such infinitesimal deformations of complex structure. We prove the following statement. Lemma 1. I decided to repeat the previous lecture a little. That B of Z, Z bar, is tensor of the sound type. Is tensor of the following type. First of all, we checked what happens if we change coordinates, make a holomorphic change of coordinates. Then B has the following transformation law. Lemma 1. Lemma 2. Of course, assume that we add this term. But of course, we have group of changes of coordinates. If using the change of coordinates, we can remove this term. It's trivial transformation of complex structure. we simply change coordinates. Therefore, of course, we have to factor this space by the space of transformations of complex structures generated by changes of coordinates. Remember. The moduli space is a factor space. All possible B factorized by the image or the transformation of complex structures generated by coordinate changes, global. And we proved that transformation is trivial, deformation is trivial, have trivial deformation of the complex structure if and only if Z bar, I'm sorry, Z bar. There is a delicate moment. I'm sorry, but okay, let's hope I will find some choice. This is a delicate moment. Because we have such operator. Of course, generically, we have to write covariant derivatives. But due to the fact that it's operator of this type, tensor of this type, there is no need to write covariant derivatives. You have no correct terms. So it's well-defined operation. Exercise, it's well-defined operation. Therefore, we have the space C 0 D bar, such D bar operator. It's called Dolbeault operator. You see. Have Dolbeault operator. Therefore, have Dolbeault operator. Therefore, the moduli space, tangent space to the moduli space, is a factor of the point gamma, the is factor we prove the following. So we have to factorize this space by the image of this map. Factor space is a tangent space to the moduli space at the curve gamma. Of course, you make calculation for a fixed curve gamma. Is it okay?
This moduli space?
Yes. Tangent, of course, the tangent space to the moduli space. Not the tangent, tangent plane. We consider deformation at one point. We don't discuss global structure. Moreover, topology of the moduli space, it's excellent area of activity of the last decades. You remember, using Witt and conjecture and so on. It's very, but I don't want to discuss this very interesting but rather complicated topic. I only want to calculate dimension of the space. First step. Some very more classical results. The statement is, we have a fixed curve gamma, and we calculate the tangent space to the moduli space, you understand? We don't discuss the global structure. We calculate only the tangent space to the moduli space. You consider deformation of a fixed curve. we fix a curve and we consider the following deformations of complex structure. So deformations are these Beltrami differentials, factor by the image of this map, by trivial, factor by trivial. Now, and we did the following. How to calculate this image? The idea was the following. Consider the adjoint operator. Adjoint operator. Adjoint operator will go okay, let's know this operator star. It's a joint. Therefore, you have this operator, you have a joint operator. Okay, you can check the lemma in linear algebra. You remember, the previous lecture I told about Fredholm alternative for linear equations. Okay, let me remove it. Okay. So we have equation A x equals to y. What is necessary as sufficient condition for solvability of this equation? Linear algebra, simple linear algebra. Have you considered the problem in linear algebra? Recognize it? Ordinary linear equation. What's necessary? But A is rectangular operator. The equation has solutions if you have to consider a joint operator. You simply transpose the matrix. You consider the kernel of the adjoint operator. And y should be orthogonal to the kernel of the adjoint operator. Necessary and sufficient conditions for solvability of these linear equations. I'm sorry, it's first year linear algebra. Theorem, I don't prove it, but nevertheless, in this case, the same is valid. Sorry, I don't want. It will be some analysis. I don't want to go into this analysis. Believe it. Here, the same result is valid. Elliptic operator, for elliptic operator, the same is valid. Therefore, we have this. But what does mean the kernel of this operator? There are exactly holomorphic two forms, you remember. We calculated the dimension of the space of holomorphic two forms. Understand? Here we calculated. It was 0, 1, 3g minus 3. It was a dimensional space of holomorphic two forms. Therefore, it's the space of the Moduli space. But now I would like to discuss some more explicit realization of the action of the Moduli space. Because I think at your lectures we had often the words Virasoro algebra. Remember? I would like to show the origin. Today will be Virasoro algebra with zero central charge, Witt algebra. The action of Witt algebra. How the Witt algebra acts on Moduli space. The formula, the formula from the book by Schiffer and Spencer. So, first of all, consider the following transformation of. First of all, since we have Riemann's slightly different object. What do we have? Okay, we have objects gamma, G, P, P0, Z. So we have the following objects. We have Riemann surface of genus G with a marked point P0, local parameter Z, near P0. Assume that we have a little more. We have Riemann surface with a marked point and local coordinate near this marked point. Moreover, we have also this condition that at the marked point the coordinate equals to 0. And moreover, assume that we have a circle. Infinity. And we assume okay, side will be the circle, defined by, for example, without loss of generality, you can assume that this circle is defined by the condition z equals to 1. Absolute value of z. Circle. Then, what defined Witt algebra? Witt algebra is a form algebra. LK dz. Of course, these vector fields are defined near this contour, near the contours sigma. Defined near this contour. We don't know if they can be extended to the whole Riemann surface, usually not. And of course, they are meromorphic at the center, because K may be either negative or positive. So we don't assume that the fields are holomorphic outside neighborhood of the contour. But they are holomorphic near the contour. You recognize this?
Sorry, what is sigma?
Contour, this. Contour.
Okay.
You have contour, sigma. So you recognize, I don't have to explain that Virasoro algebra with zero central charge. Is it clear? Sorry. You recognize it. Now, consider the following transformations of the complex structure. The following transformations of the complex structure. Assume that we glue gamma is a result of, consider two pieces. Gamma minus is obtained by removing a hole. We cut a hole from gamma. Hole may be something like you see, a little smaller than 1. So the unit contour is here. Inside sigma, yes. Inside sigma. And it's gamma minus. And gamma plus will be this area sigma. You see. It's a patch. a patch. And of course, gamma is obtained by gluing some points. What is gamma? Gamma is out of gluing. So we made a hole and we add the patch to the Riemann surface. Okay? But now, how it deform complex structure? Let's change the gluing law. Now,
Gamma plus is just this page of this is just this disk, yes?
yes, disk.
This less than 1 plus delta.
Yes.
And then we glue it with gamma light.
Yes. Okay, let me magnify a little the picture. Sigma. Disk sigma. This is the hole, you see. Hole is a little small, but we removed. You have this annulus, and we have this disk. It's sigma. You see. Sorry, the picture is clear. And we have the gluing law. The point x minus close to point x plus.
X plus is minus x minus.
The same point. But the same point. At this part we denoted x minus, at this point we denote x plus. But it's the same point on the original Riemann surface.
No, okay. If x minus equal 1, x plus equal minus 1, yes?
Equals 1 also. I'm sorry, maybe it's wrong picture. Yes, I'm sorry. I'm sorry.
I understand.
Yes. In the coordinates z of x plus is equal to z of x minus.
And there will be overlap, yes? When we glue,
Yes.
since our hole is smaller than our page,
Yes.
we have some overlap.
Yes, you have this area. This area is glued to this area, you see. You glue this area to this area. I don't want to glue. If you put a patch, you have some overlap, you agree? You have some overlap.
1 minus delta.
The 1 plus delta.
1 plus delta.
No, minus delta, the same. No. We glue this, we glue to this. No, this, we glue to this. This, we glue to this.
Okay. Trivial glue.
Sorry.
No,
Yes, we simply glue.
okay.
But now let's introduce a new surface. we have vector field. How to introduce new? We have vector field V. And now we glue this point to the shifted point. We have vector field. And we glue the. Now we have a new gluing law, we glue to this point. We consider first order small deformations, therefore we neglect high order terms. Understand? We change the. We move the patch a little before. Slightly move it. But in fact, I prefer to move this, not this.
Little twist.
Little twist, yes. But maybe little twist, little dilation. Some, of course, you can move this way. Don't. Maybe
There's vector, the vector field V.
any of this,
Okay.
any of this element, any of these vector fields. So we have vector field, and each vector field, and the vector field some linear combination of these Virasoro elements, maybe the basic Virasoro element. You understand? But okay, it's geometric construction, but we would like to have some to make some calculations. Let me show how to do calculations with this construction. Because, of course, it's geometric construction, but you may say that it's like waving hands. How to calculate using this construction? Let me explain it. Well, let me explain the calculation. First lemma, important lemma. Lemma 1. What is, how to describe tensors of functions on the new Riemann surface gamma? In fact, on gamma tilde, we have some discontinuous system of coordinates. We can introduce some system coordinates which has some discontinuity. Why not? Because we map a function from gamma tilde to gamma. If a point is inside this area, we move to map to gamma minus. If it's here, we move to gamma plus. But this coordinate system has discontinuity on the contour. And what is the equation? F agree. So, because at new Riemann surface, we glued these points. It's the same point. But on the old Riemann surface, we have these continuous functions. Sorry. So we have point x minus x minus. And now it's attached to a new point, x. You agree? So the function here equals to function here, because we have discontinuous system of coordinates. So you have something like this, you see. you see that.
The glue, right?
We change the gluing law because now we have deformation of the figure, you see. Because we see something like this. Understand? It is continuity. This point should be continued here. Somewhere here, you see. You obtain some so. But it means that we have the following equation. It's the same point of the boundary. LV means lead derivative. For functions, ordinary derivative with respect to V, but I prefer to write lead derivative for tensors. You see? So we obtain this discontinuity. You see? So regular tensors on the new Riemann surface can be interpreted as tensors on the old Riemann surfaces with the following discontinuity as the contour. Okay, is it clear? So we have to solve the problem. We know discontinuity, and we have to reconstruct the yes. So first step, maybe the most important. We reduce the problem of calculated, so the tensors on the new vector field, regular tensors on the new Riemann surface, are tensors on the old Riemann surface, but with discontinuity as the contour of this special type. First, okay, first step.
Sorry, why this lemma? Why not this definition? F 1x plus imply epsilon v.
Sorry, why did not start from it or not? Sorry. No, it's important.
This inequality is equal. Why not?
Sorry, what does it mean equal? It's non-trivial relation. Very no, it's very non-trivial relation, but simple, but very non-trivial.
Oh, non-trivial. Okay.
Okay. You think that it's trivial. It's okay, but it's important. Okay, maybe it's easy, but important. Here's this important relation. Okay? Now, may I remove this figure? Next, intermediate step. Assume that we have functions on the Riemann sphere. Assume that we have a contour. And we would like to solve the problem because we have a prescribed discontinuity. How to construct a function in the complex plane. Let's start from the complex plane. Complex plane. With the prescribed discontinuity, we have unit contour or some contour. And we have f. It's x minus maybe minus x plus. It's not important. The problem, how construct a function f which is holomorphic inside the contour, outside the contour, and have the prescribed discontinuity at the contour? The answer is, okay, we can assume that function vanishes at infinity. Extra requirement, not difficult. Right. We recognize Cauchy formula from the complex analysis. What is the difference? Okay, we can also write this way. Minus, okay, this. Now, of course, what is the use of the complex analysis? Assume that function is 0 outside the contour and holomorphic inside. Then we have the Cauchy formula, you agree? But what if we apply Cauchy formula to arbitrary function g? This formula defines the function which is holomorphic outside and holomorphic inside the contour. And the jump is exactly this one. It's Plemel-Sochotsky formula also. Is it clear? So this is how to solve. But now we have, first of all, what I would like to do. I would like to calculate the variation of the Riemann matrix. Understand? So I would like to calculate the variation of differentials. How to modify this Plemel-Sochotsky formula? Assume that we have differential omega j. Assume that omega j is one of the basic holomorphic differentials. Remember, we have basis of holomorphic differentials. We assume that we have basis of cycles. We have basic of holomorphic differentials. We have this basic of holomorphic differentials. Now, we modified the complex structure. So now we have equation. Now, the holomorphic differential of the new Riemann surface, omega tilde. What is the properties of omega tilde? It's the form differential. Again, we have the same identity. G. But on the contour, you have relations. You see the difference between omega and omega tilde is of order epsilon. You agree? You have small infinitesimal deformation of complex structure, you have infinitesimal deformation of all objects. Therefore, in the first order calculation, it's enough to write this one. Agree? Okay? So is it clear? I repeat the following. How to define differential omega tilde?
Sorry, no symbol at epsilon square? No.
No, it is exact identity.
Omega minus omega tilde equal
No, it's deformation of order epsilon.
epsilon. No, epsilon square.
Oh, epsilon, of course, epsilon.
Or
You have first order of... You have epsilon, we calculate everything in the order epsilon. And we forgot about epsilon square terms. Epsilon, epsilon. Sorry, is it okay? Because, of course, we can write omega tilde instead of omega, but it will be epsilon square. It's epsilon, it will be epsilon square correction. Plus, okay. If you like, okay.
I don't understand. This we get errors.
No, of course we have
epsilon,
epsilon deformation of our Riemann surface. So all objects are affected of order epsilon. Epsilon
Yes.
change.
Okay.
So is it clear? We simply applied this formula. Now, we can simply write minus epsilon 2 pi I Sorry, of course, I've forgotten that. You recognize the previous formula. I wrote 5 minutes ago, generalized Cauchy formula. And what does it mean? But what is omega capital? May I remove this? First of all, we consider deformation of differentials. So omega capital should be differential by lambda and function psi, because this is differential. We integrate over contour. I'm sorry, I forgot to write this way. The previous formula, a generalized Cauchy kernel. First property. Because you remember, in standard Cauchy formula was omega, standard Cauchy kernel. You remember, we apply this Cauchy kernel to functions. Therefore, it was function lambda and differential psi. But here we deform differentials, not functions. Because we deform differentials, not functions, we have to change the type of the kernel. It will be form in lambda and function psi, you see, locally. You see. Of course, differential could not have exactly one first order pole, you remember. It should be set kind differential. Therefore, that's permitted. Where lambda goes to this point P0. You see. If lambda, okay, we work in the coordinate where lambda goes to 0. So for each fixed psi, lambda is set type differential. And also we have this condition, you see. Therefore, these integrals of the object over a period should be 0 of this. Don't change the integrals over a period. It means that omega you understand? So for each lambda, we have exactly one differential of the set kind with this normalization. Omega is exactly this differential. The only variation with standard complex analysis is differential form in lambda, differential in psi, instead of this. Because we apply to forms, not to functions. And then automatically I'm sorry, maybe I used too much, but okay, let me remove it. From this formula, you automatically update. You have to integrate this. Over bk. So we have to integrate, you understand the formula, we simply have to integrate the object over bk to obtain the new Riemann matrix. Integral of the new form over the cycle bk. Okay? So we have to integrate this by lambda over, I write over bk, and then we have this object. Agree? So is it clear? We simply deformed the form and we integrate the deformed form over the cycle bk. So far, so good. Next step. Oh, sorry, may I remove it? May I remove it? No. We have by linear relations.
Sorry. Capital BKJ equal BKJ small.
Yes, maybe small. I don't pay. Yes, maybe small. Riemann, yes, B. B. Okay, so you have this. Now, we can calculate. Let's calculate this integral. Integrate with respect to lambda. From Riemann bilinear relations, we have equals to shall I repeat the calculation or not? Okay, maybe this linear, as we proved this lemma, you remember. We have a third kind differential, these 2 points. If we apply linear bilinear relation to this pair, this differential and differential omega k, you obtain this identity. Sorry, minus. Oh, okay, let me repeat it. Consider the following form. Consider the following form, you remember. From one point of view, the integral will be sum of First of all, these integrals are zero by definition, you remember. Therefore, due to this property, this term vanishes. This is delta function, so it will be exactly that. I'm sorry, let me write it correctly. Sorry. For example, we obtain the following expression. Sum over L equal to 1 to G AL omega K integral BL omega minus BL omega K You remember, the integral over the boundary was this one. You remember it? It was exactly you remember. Because this is delta function, this is 0. From other point of view, we had on the right-hand side, we have 2 points, p minus p plus. The residue of omega capital is plus 1 hair minus 1 hair. So this product is integral to pi I So this integral is 2 pi I omega at this point minus 2 pi I omega at this point, primitive of omega. So it will be 2 pi I p minus. It's exactly this integral. Okay? Riemann by linear relations. So we have this formula. So far, so good. May I remove this? Riemann by linear relations. But what we obtain? That we obtained the following formula. Plus epsilon the primitive of omega k times LV omega 3. Okay? So you see that we come to a nice formula. You agree? So, any question about the steps? First step, we reduce geometrical condition to the Riemann-Hilbert problem for reconstructing function from the discontinuity on the contour. Second, we write solution of the Riemann-Hilbert problem using generalized Cauchy formula. Third step, we calculate this integral using Riemann bilinear relations. So I think everything is okay. It is based on the previous technique, but I think all steps are clear, I hope. Now, yes, I have exactly 15 minutes, and let me finish. May I remove it? Now, next formula. May I leave it as exercise? That LV of omega is no, maybe I will prove it. Why not? Why not to prove it, by the way? Why not to prove it? Because what is a lead derivative? We have Remember, I wrote the formula for the lead derivative. But moreover, if you have oh, sorry, this no, I'm sorry, but here you have this formula. No, but okay, but in this case, what we have? In this case, we see that we have the form we have only one variable. We have only one variable. And because we have only one variable, we have here one term, you see. So one variable, this is. Therefore, we obtain that we can integrate by parts. We have the formula. Remember, we have the formula for integration by parts. Therefore, finally, we obtain the formula. Okay, let me clear everything and formulate the final answer.
Sorry. What is delta?
Okay. We write this way. Let's use this notation. Yes, variation. So we obtain the found formula. You agree, it's a very beautiful formula, finally. Because we started from very geometrical object. It can be found in the book by Schiffer and Spencer, Function of Riemann Surfaces. This formula can be found. Of course, depending on the orientation, sign will be plus or minus. But you see, very beautiful formula. But in some sense, you can treat the following. You have vector field as Beltrami differential. Which is local delta type, the Beltrami differential, localized on the contour. And it's conjugate. But it's a little delicate. I hope at the exercise we discuss something. So this aim of the lecture was to prove this formula. Yes. Maybe I wanted to show you how to, because the situation is the following. We have very geometrical construction, you agree. The problem, how we can calculate anything with the geometrical construction. Again, the basic equation, what's the variation of basic differentials, and what is the variation of the Riemann matrix, period matrix. So I showed how to do the calculations using bilinear relation. There are two main ideas. One main idea that reduce the geometrical construction to this equation, to go from geometry to analysis. This equation is away from geometry analysis. The second, we used bilinear relations to calculate the variation of the period. And also, third step was to use proper modification of the Cauchy formula. To use a proper modification of the Cauchy kernel. It's an important question. It's a little long story, but nevertheless, what are the proper analogs of the Cauchy kernels? And we use the fact that the existence, uniqueness, differentials of the said kind with two prescribed poles. Maybe it's formally it was necessary to prove that everything holomorphically depends on lambda, but it's so, it's true. Let me omit it. Everything. But it's okay. Therefore, I would like to finish today's lecture. I would like to provide one extra lecture, and in this lecture, I will try to explain the origin of the Virasoro algebra, the origin of the central charge. Because I remember at your lectures you will always have Virasoro algebra. In this construction, we have Virasoro algebra with zero central charge. Let me show the origin of non-zero central charge. So, what was the main purpose of these last two lectures? Because I think in this course you always had Virasoro algebra, some very, very important object, you agree. I wanted to relate Virasoro algebra to the conformal. Moreover, one of the purposes why this design, the idea was, if we consider string theory, we have to integrate over conformal classes, over complex structures. Therefore, to integrate with the complex structures, we have to integrate it. So we have to know the dimension of space of which we integrate first. And then, okay, so integration of the moduli space, it was one of the basic ingredients of the conformal field theory. I remember Vadim Knizhnik, unfortunately, you know this, it was a very sad story, but Vadim Knizhnik, he was 27, he made few excellent, brilliant works, and suddenly his heart stopped in metro. They were riding metro, and his heart immediately stopped, because he was physically strong, he was a healthy person. Maybe he worked too much, maybe, I don't know. But I remember, I observed that this excellent, beautiful story, how it started. Nevertheless, and therefore, the aim of the lecture was explained why the origin of the Virasoro algebra. It was zero central charge, not zero central charge. I will demonstrate next Wednesday. It will be the last lecture.